Welcome to average rate of change, conclusion. And let's take a look at two problems. A remote control car travels a distance S of t equals 10t squared feet in the first t seconds after it starts. Calculate the average velocity of the car on the interval shown in the table below. Right? So when we're calculating, we will be finding, go ahead and write this, average rate of change is going to be S of T1 minus S of T2 divided by T1 minus T2. So for each of these, we would plug each of the T values into the formula, find the value of the equation at those T values. In the numerator, we would take the difference of those values and then divide by the difference of the values of T. And that could be looking nicer. There we go. Sorry, it's a little wavy over there. All right. Our purpose is on this particular problem is to be looking at what happens as those values of t get closer and closer together. Not to necessarily be practicing calculating out average rate of change. I want you to write the formula down, and I use that formula to calculate all of these average rates of change already using the values of t for each interval. Right? So rather than us doing that together and having you write that down, let's write the final results because we want to look at we want to analyze the values in the table. All right? I think we're all clear on how they were calculated now, and let's just go ahead and fill out the table. So for T1 T1 2 and T2 1.99, I got 39.9 feet per second. And then for the second interval here, 1.999 and 2, I got 39.99. And for 1.999 and 2.001, I got 40. For 2 and 2.001, I got 40.01. For 2 and 2.01, I got 40.1. And 2 and 2.1, I got 41. So as the values get closer together, we start to see that the values are getting very close to a single number. All of these values are pretty close to 40. And as we look from the left, as we looked at the table, looking at the center value there, from the left and from the right, our values seem to be centered on about 40. So based on our calculations, can you approximate the exact velocity of the car at 2 seconds after it starts? So the velocity at t equals 2 seconds is approximately 40 feet per second. Actually, I'll write the word per. Notice we still said approximately because we can't calculate it out exactly. We can't, so exactly would mean that we would have to use 2 and 2. And that would be a problem because we would have 0 in a denominator. We just have 0 over 0, right? And that wouldn't have any meaning. But what we did was we chose values that were closer and closer together to approximate the exact velocity of the car at 2 seconds. The more decimal places we use, the closer the values were. So that brings out an important point. Exact velocity is also sometimes called instantaneous. Instantaneous rate of change. Oops, missed a syllable there. Instantaneous. It's hard to write and talk at the same time. Instantaneous. Yeah, instantaneous. Yeah, got it. Rate of change or velocity. And a big idea is that average rate of change approximates exact or instantaneous rate of change. The closer the values of x, and x being the independent variable, the better the approximation. So go ahead and add that to your notes. So if I have an equation where I can plug in any value I want, right, I would want two values that were very, very, very close together. So for instance, if I wanted to approximate, if I wanted even better approximation, I could use values that were even closer. Like, so if I wanted to approximate 3, I could use 2.9999999 and 3.000001. Right? The closer those are, the better the approximation. If we have a table and we can only choose values in the table, we wouldn't pick the endpoints. We would pick the two values that were the closest on either side to the value we're actually looking for. I can't really use this table as an example because I have intervals, not values. But if we were to think of one of the other, I know we have another table in here. I do believe. Didn't we do a table? Just one, there was a table in here. Oh, here we go. Well, that was classwork. That's okay. So if I wanted to approximate 24, which is not in the table, this top table up here, I wouldn't choose 3 and 55 because they're not not as close as I could get. I would choose 10 and 43 because they're much closer to 24, and I could use that to approximate the average rate, the instantaneous rate of change at 24. Now, if I had even closer, not those two values, these two values. If I had even better values, right, closer values, then I would choose those. So we can approximate average rate of change with instantaneous rate of change with average rate of change. But closer values are better. All right, now I have to do this. All right, let's take a look at this one. I did a little bit of the so first of all, let's look at our formula. The traffic flows at a particular intersection is modeled by the function f, defined by f of t equals 96 plus 5 sine t divided by 2 for t between 0 and 30 minutes. So that means that this formula could be used for anytime up to 30 minutes. But then it perhaps isn't a good model anymore. So that we wouldn't use it if we were interested in 1 hour, right? Because this was specifically for 0 to 30 minutes. This is not a problem you could, so these aren't computations you can do in your head. These are computations you need a calculator for. They are not friendly values for sine. So, yeah. And when you calculate in this class for trig functions, make sure your calculator is in radians. So first, we want to find the average rate of change of the traffic flow over the time interval from 3 to 8. So I'm going to put f of 8 down first, because when I do the computation, I'm going to have, of course, f of 8 minus f of 3. Now, there's no reason you can't have f of 3 minus f of 8, so long as you have 3 minus 8. But I don't know. I always put the larger number in first. And f, I have it in my calculator. Oh, there it is. So I just did 96 plus 5 sine, and then 3 divided by 2 is 1.5. So I got 100.9875. And then f of 3, or excuse me, f of, oops, I'm sorry. I wrote f of 3 next to f of 8 because I plugged that first in the calculator. So f of 8 was 92.2159. And f of 3 was 100.9875. Right. So those are the values when I plugged it into the calculator. And it's really hard to hold a calculator, so I'm going to put it down. Well, hard to hold the calculator and a pen in one hand and a calculator and the microphone in the other hand. So for average rate of change, we want to find f of 8 minus f of 3 over 8 minus 3. So that is 92.2159 minus 100.9875 divided by 5. And let's just write the final answer here, which is 1.754. I just put in 3 decimal places. Here, 9875 divided by, so if you want the 4th decimal place, give me 1 second. It was a 3. I didn't write that down. There we go. Oh, excuse me. I forgot to write that down. Negative 1.7543. Indicate the units of measure. Right? This is a problem in context. We need units of measure. And this is vehicles per minute, because the function is measuring traffic flow. Those are vehicles. I wouldn't put traffic per minute. How do you count a traffic, right? What is 5 traffics? All right, I know what 1.7543 vehicles means, right? It's a little more than 1, a little less than 2 vehicles per minute, right? But traffic, that's not a unit. That's, right? So it does not have to be a word in the sentence. You got to use a little common sense that traffic is vehicles. I also wouldn't say cars per minute. Too narrow, because you could have buses and trucks and motorcycles, and I don't know what else you could drive on a car or through an intersection. And then T is time in minutes, and you do not. So minutes is perfectly good units for us. Now we need to explain what this rate tells you about the flow of traffic during this time. We want to be as specific as possible, and I'm running out of space. So I am, where am I going to write? I am going to write up here because I need all of the other space already. So I'll write up here. So traffic flow is, since it's negative, it's decreasing. Above that, I'm just going to put ARC is negative to remind you why, by and we're going to round on this, 1.8 vehicles per minute from this is, so we want to be specific, right? Because it's not always going to be consistent, right? If you plug in 2 different times, you're going to get a different value. So this is from 3 to 8 seconds. All right. So you might think, oh, I rounded quite a bit, right? I've got a more exact answer below. I've rounded a little bit because, well, it's not like I can have a part of a car going through. We're just not having as many as 2 cars per minute, or it's not decreasing by as many as 2 cars per minute, vehicles per minute. It's decreasing by a little bit less than that. So I just rounded it to just the 1 decimal place. I wouldn't say 1 and I wouldn't say 2. 1.8 for the explanation, because I've already got a more exact answer in the work, right? So I think it would be fine to write 1.8 vehicles on the explanation. Now notice I didn't put it's decreasing by negative 1.8 vehicles. Don't put the negatives in when you're explaining, right? When you're explaining, put increasing, decreasing, right? The increasing says it's positive, the decreasing says it's negative, right? You don't need to make the number negative, right? It's understood by the question, right? If if your bank account decreased by $5, you would say my bank account decreased by $5. You wouldn't say my bank account decreased by negative $5. What does that mean, right? Is it possible to find the rate of change at a specific time? Why or why not? If you think back to that last question, you can estimate over a very small interval to approximate the exact, I'm going to put average rate of change, right? Rather than write the words rate of change. You cannot calculate at a specific time. Because, actually, I'm going to use the symbol. Save an inch of space. It would cause division by 0. Right, so I can't have t of 5 and t of 5. Right? Otherwise, I got 5 minus 5. That's 0 in a denominator. That's no good. Right? But I can estimate, I can approximate, and the closer the values are to each other, the better my approximation is of the exact rate. Now let's explore the rate of change at 2 intervals over small intervals. Estimate the rate of change of traffic flow at t equals 8 by finding the average rates of change from 3 different intervals. T equals 8 to 8.1, t equals 8 to 8.01, and t equals 8 to 8.001. We're going to set it up, and I'm going to give you the average rate of change. Right? We're not going to have all of the computations in on this one. I don't think we could fit 3 of them, quite honestly. Me either. Plus, our goal is to explore what happens to the average rate of change as those values of t are getting closer and closer to one another. Because 8 and 8.001 are closer than is 8 and 8.1. Right? The first 8 and 8.1 differ by 1/10. 8 and 8.001 differ by 1/1000th. All right, so they're quite closer. So we have f of 8.1 minus f of 8 divided by 8.1 minus 8, and that equals negative 1.586. When we're calculating these, please do write the formula, because that says what it is you're doing. Right? It gives meaning to these values. All right, now we got f of 8.01 minus f of 8 divided by 8.01 minus 8. And this time I got negative 1.629. By the way, we'll put the units in D when we explain the meaning. We're going to leave the units off. Plus, I don't have enough space to write vehicles per minute for every single one of these. And then we have f of 8.001 minus f of 8 divided by 8.001 minus 8, and I got negative 1.634. Explain the meaning of your findings in Part C in relation to the traffic flow. At t equals 8 minutes, the traffic flow rate is about negative 1.63 vehicles per minute. So here I'm just stating what it is. And that negative 1.634, remember, that's an approximation, right? Because I'm looking at 8. I want to know what it is at t equals 8, but I can't use 8. I have to use 2 numbers that aren't 8, otherwise I have 0 in a denominator. So I used 2 numbers that are close, 8.001 and 8. Right? So you can drop that to 2 decimal places and drop off that last one because we are approximating here. And I have the negative in here because I'm just stating the value along with its units. Now, what does that mean? It means traffic flow is decreasing by 1.63, or I can put 1.6, but I'll keep the same units. Same values. 1.63 cars per minute. Oh, excuse me, vehicles per minute. At t equals 8, it was seconds, wasn't it? Or minutes? Minutes. Trying to remember my units. All right, let me make sure my sentence made sense because I'm writing at the same time. At t equals, actually, I've already said t equals 8 twice. So let's put at this time. That makes for a better sentence. All right, so at t equals 8 minutes, the traffic flow is about negative 1.63 vehicles per minute, meaning traffic flow is decreasing by 1.6 vehicles per minute at this time. All right. So we have finished looking at average rate of change, and we'll be continuing looking at our specific functions. So thanks for watching, and bye for now.